Hey everybody, welcome to part 2 of Noob Tig welds. And I was just going through sorting all of my little cut-off pieces there and actually putting them into the correct size packages. I was wondering out loud to myself, how short of a piece of tungsten how short does the tungsten have to get before it's pretty much not usable any longer? I mean, you know, like, here's a 1/8 inch thoriated piece. It's probably about 3.5 inches long, and I could regrind a tip on it. So I would say that that's probably still usable. And for a noob like myself, who's probably going to spend a lot of time accidentally touching the weld puddle with the tip, which instantly contaminates the tungsten, probably wouldn't be a bad idea for me to hold on to some of these shorter pieces to a point. Alright, so this pile right here, this is a pile that I'm tossing out for the most part because most of them are really short pieces that there's no color band left on them. So that one there is definitely a pure tungsten, but it's so short. Once I grind all that crud off of there, it's going to be just a little tiny, like 1-inch piece. So, and a couple of these other ones here are, you know, even this one here has got some length to it, but it's bent, and I don't know why, but there's a grind mark there. And so just gonna toss these. But I was just wondering, how short do you think you can keep one? Like, here's a 1/16 of an inch, I believe. It's got a red stripe on it, so it's a thoriated, so I'll keep that one. And then these two pieces right here, I actually inadvertently thought these were tungstens, but then when I looked at them on the magnification and looked at the ends, I realized that these are actually small, thin filler wire. Not sure what makeup they are, but I figure, okay, when I'm playing around, I'll try and use those. And this little stack right here, I can't bring myself to throw these out because these still actually have some usable length to them, but none of these have any bands on them, so I have no idea what the composition of those is. So I figured maybe I'll just experiment with those. Alright, so now I'm going to talk about grinding tungstens. There are 3 basic points or shapes on the end of a tungsten that you want, depending on what type of work you're doing. A ball end, which is self-explanatory, a small ball on the end, which typically is done by actually, once you fire a pure tungsten and you get the amperage up high enough, it'll start to actually ball on its own. That's what, like we talked about in part 1, some tungstens ball up more readily than others. Secondly is just a point, okay? But you also have, so you can have a point like this, okay? And then sometimes what some guys will do is they'll grind a flat on the end. So they'll take this little tiny tip right off and they'll grind a little flat, and that's called the truncated tip, okay? So they end up with something more like that. Now, whether or not you want to do that or not really depends on, well, what size tungsten are you using? What application is it being used? Are you putting a lot of filler metal down? So there's other variables there, and best thing I could say there is probably experimentation. Find what works for you. Grinding tungstens, and I'll get to grinding wheels and things like that in a moment. But the important thing to realize about grinding a tungsten is that when you grind a tungsten, the way that it's going to be on the wheel, you want to make sure it's oriented so that the grinding marks that you end up with are running, this is our tungsten here, right? Are running along the length of the tungsten like this. In other words, you would never want to hold the tungsten like on the side of a wheel, or even hold it sideways to a wheel, because you're going to end up with grind marks going across like this, or worse yet, like this. If you grind your tungsten so you end up with marks like this or like this, the arc may want to try and wander on you. Whereas if you grind it so that you stay parallel to the central axis of the tungsten, you're going to have, or at the very least, if they're somewhat pointing, if the lines, the grind lines are basically pointing out towards the tip, which is pointing at the work, you're going to be happier. And I'd like to say I could tell you that from experience, but again, this is TIG welding noob, so I'm just going on what I've read online. I even just read about another guy in a Miller post. He talked about that he saw an article in Classic Car magazine about TIG welding, and that in the article they actually said, no, you want to actually go, you want these grind lines perpendicular. And that led to a whole discussion about how, well, that goes completely against everything that everybody else had heard or been taught over the years. So there was a question of whether or not it was an error on the part of the person writing the article or what. But I'm not going to get into that. I'm just going to go with what I've been told, which is this. Okay, so that means quite simply that if I'm going to grind my tungstens on a grinding wheel mounted on a bench grinder, I was talking about how I'm going to hold my tungsten. So there's basically, you could hold it like this and rotate it as you're grinding. Okay. Or you could hold it like this. Okay. And rotate it as you're grinding. This is nice because the wheel's running this way. So if you happen to lose your grip, tungsten will go this way. This way, if you dig in a little bit too much, it might want to drive the tungsten out of your, or into your hand. Then you're going to be like walking around with a tungsten sticking out of your hand. No, seriously though, this is the way that I think most guys prefer to do it on a bench grinder, because you get a really good look at the angle and the point that you're creating. Another trick guys talk about, that they literally chuck the tungsten up in a cordless drill and spin it as they're grinding it. I would say if you spin it too fast, you're going to end up with grind marks that might be kind of like swirled around, circular around the tip. So I don't know how well that may or may not affect your work. So anyways, that's the idea. And then of course they have special tungsten grinders that are dedicated grinders for grinding tungstens. And they have some cheaper ones, like Radnor makes one that's probably around $70. It looks like they literally took an angle grinder and like put a special head on it that just has a place where you insert the tungsten. And anyways, then they have really dedicated ones that have their own little hopper that keeps all of the they have water in there to cool the grind. And they have a little hopper in there, and it's all self-contained and keeps all the grinding dust in there. But those can get crazy expensive. So if you're not in a professional welding shop, I doubt you're going to get one of those. And the typical weekend warrior is not going to do that. So the other important thing is that the grinding wheel that you use to grind tungstens should be used exclusively for only grinding tungstens. Because if you just go over to your regular grinder, whatever metal was last ground on that grinder, some of that metal is left behind in that wheel. And then you come along and you go to grind your tungsten, some of that metal is going to transfer off of that wheel and back into your tungsten. You're going to contaminate your tungsten. So you don't want to do that. So you want to have a wheel that's dedicated. So what I'm probably going to do is I've got a little homemade bench grinder. So this is a contraption that I made quite some time ago. This was actually an old Continental, Continental sounds so great, but this was made in Taiwan, cheapo junk bench grinder that burned up. And instead of throwing it out, I had some of these little motors right here And this is an AC motor out of a Whirlpool bath pump. And the motors worked perfectly fine. And I was like, well, maybe I could do something with this thing and use it for something. So I basically made an adapter so that I could use it on there. And I just figured a way to mount it inside the original case. And it actually works pretty well. And then, unfortunately, this cheese bag switch broke. So I just bypassed it. So now it just turns on as soon as I plug it in. And what I've got on here now, I really don't use it anymore, but what I was using it for was, I've got a soft bronze or brass wheel on there, brass bristle wheel, and I was using this for delicate parts. Anyways, getting off the subject, but I'll set this up with a grinding wheel, and I'll turn this into my own personal exclusive TIG grinder. And they have wheels that are dedicated wheels for especially formulated for TIG grinding, and they can get kind of expensive. So what I'm probably going to end up doing is just getting out of all these extra wheels I got laying around here, I'll find a clean, good wheel that fits on there, slap it on there, and go to town. What grit do you want to use? Well, ideally, you want to use a coarse grit for removing a lot of material quickly, but then you want a fine grit for cleanup. So ideally you would have two grits. I saw somebody say that what they like to do is they like to use 80 grit and 240 grit. So the 240 grit is nice because it gives a nice polished finish and takes care of a lot of those grind marks and makes them really fine, which helps with keeping the arc from wandering. The problem with a 240 grit wheel is you'll be sitting there all day trying to grind a tungsten if you're starting with, oh, say, you know, a tip like that, and need to go to you need to cut it to its initial point. So the idea being is you would do the heavy work with the 80 grit wheel, and once you got pretty much finished, you would clean it up on the 240. Some guys, very experienced welders who've been welding for a long time, they throw all that out the window and they say, geez, I guess they're, you know, saw in the forums they talk about, boy, I guess I'm old school, because they talk about how just get an angle grinder. They take an angle grinder. One guy puts again in a drill and runs his angle grinder and spins it in the drill up on the angle grinder, and he's done. So anyways, I think I covered. Okay, oh yeah, so the other thing I want to talk about with grinding, of course, with grinding, eye protection, always. But the other thing is, a lot of guys, including myself, are guilty of grinding things and not wearing a dust mask. And you definitely do not want to breathe in the dust produced when you're grinding tungsten, especially thoriated tungsten. Thoriated tungsten dust is radioactive. Remember, we talked about it's not so radioactive that it's going to, you know, be a danger for you to just hold it in your hands, so to speak. But if you breathe radioactive thorium, you can end up with lung cancer. And there are some guys that are just, oh, I've been breathing that for years, never. Hey, you know what? Great. You won the genetic lottery, maybe. I know a guy. He finally passed away, and he was in his 90s, and that guy ate hot dogs probably every day of his life. And there are people who tell you, oh, the stuff that's in hot dogs, they're bad for you. Well, tell you what, some guys have all the luck. Anyways, getting off the subject again. Don't breathe the dust. I'm actually never going to grind tungstens down here in my shop. I've got my bulkhead right over there. This is my basement shop. I've got my bulkhead right there. It's easy enough for me to walk outside with that little portable grinder I just showed you. I mean, I'll slap that thing out there, put it on my work table out in the backyard, grind my tungstens, and be done with it. And I'll be doing it out there in the open air and not have to worry about. And I'll probably still wear a mask because I don't want to inhale that stuff and suck it up into my respiratory system. All right. So I think I covered everything I wanted to cover as far as how to grind them, and some precautions. All right, now let's talk about the anatomy of the TIG torch itself. This is an HW20 Heliarc torch by ESAB, water-cooled torch. All right. So this, you'll notice this has 3 lines, and the reason why there are 3 lines is because of the water, the coolant. Basically, the cable that supplies the power actually is shielded inside of one of these hoses that is actually supplying the well, actually, this one of these lines is a dedicated coolant line, and then another one of these lines actually access the power cable to the electrode, but it's also the return line for the coolant. And then the last line is the line to your shielding gas. And then I've got this little, you can buy one of these sheaths right here to help protect your torch cables, because they, you know, can run anywhere from 30 to 60 bucks a piece to replace, depending on how lucky you get on what kind of deals you find. So let's take a look at the actual TIG torch itself. All right, so for starters, we have this pink thing right here is called the cup. And what the cup is responsible for doing is it's responsible for keeping that shielding gas around the molten weld puddle and until it cools. So that's why you tend to have post flow on most welders, so that the gas continues to flow even after the arc is stopped. And you'll if you've watched guys when they TIG weld, when they finish TIG welding and they stop and they extinguish the arc, they don't just pull away right away. They actually wait a second. What they're doing is they're waiting for that. They're keeping the torch nearby so that that plume of shielding gas is still protecting that molten weld puddle until it's able to actually cool enough. Anyways, you can see these little holes here. This is where the shielding gas comes out. Okay, and then we've got the cup. So depending on how big you're going, they have different cup sizes. So this is a number 5. You can see that's a lot smaller. So this might be good for maybe a much smaller, like a .040 tungsten or something like that. The larger the cup, the more area you're obviously going to be able to cover with the gas. But in order to do that, then you've got to bump up your flow rate on your gas, so you use more shielding gas. So you don't want to use too much shielding gas if you don't have to. And typically it's going to be the larger cups are going to be for the larger electrodes. So this is our electrode. This cap on the back here, okay, has an O-ring, and the O-ring's there to keep gas from leaking out the back. But this cap does 2 things. It covers the back of the electrode, obviously, but the other thing it does is it actually pulls in this part right here and gives you the clamping action. I'll show you how this all breaks down. So you notice as soon as I take this cap, unscrew this cap, now the electrode's pretty much loose. Pull this out, we got this little part right here. Okay, and then this piece right here unscrews from here. Okay, and so you can see there's nothing in there. That's it. That's pretty much the whole shebang. All right, what we have is we have this little thin part right here. It's a thin little metal tube with slits in it, and this is called the collet. And this part right here is called the collet body, because this sits inside here like this. And what happens is, when this is screwed into the front of the head, and you put this in, and then when you screw this into the back, it actually pushes this into the back side of this collet body, and there's a taper in there, and what it does is it causes this part right here, this nose part, to squeeze down and actually clamp down on the tungsten electrode. So that's how it's held in there. So we put this in like this, okay, and when this comes on the back like this, and when this is already screwed into the front and this gets screwed in the back, essentially it's going to push these two together and it's going to cause that to close down and clamp down on it. So if you loosen this a little bit, you can move the tungsten in and out if you want to adjust the stick out, for instance. But it's really pretty basic. And the collet body, in addition to being a place for the collet to actually get pushed into and tighten down on, the other thing the collet body does is it has these holes in it to direct that, to disperse that shielding gas around the inside of the cup, and then of course around your weld. Now there's an alternative to this collet body and cup setup, and it's called a gas lens. Now a gas lens has a fine screen in the end of it, and I believe that it's actually superior to this setup, but I think it's more expensive, and I think you have to use a higher flow rate, so you use more gas with it. I may be wrong on that, but I don't have one, so I can't even show you one. But gas, that's the difference between this type of setup and a gas lens. When I first started out and I was watching videos, I was confused because I thought that gas lens, I thought they were actually talking about these cups, and it turns out that no, a gas lens is actually behind the special cups that go on gas lenses. Behind that, it looks like a round, almost looks like a round screen. Of course, there's a hole in the middle for the electrode to come through, but I don't know if it's sintered or material or what it is, but it really creates an even, I guess, flow of shielding gas around that electrode. All right, so I'm getting ready to put this thing back together and do some welding, and the next thing I've got to decide is I've got to decide on the cup size that I want to use. Now, unfortunately, I don't have too many choices because right now I'm a little short on cups. I've got a whole bunch of these, which are really small. These are marked number 5s clearly. I have this one, which is unmarked, so I don't know what size that is. And then I have this one here, which is also unmarked and is the largest one I currently have. So how do I decide what size cup to use? Well, from what I can gather, again, by going all around and searching and reading all different things, there's a lot of different opinions, and there's a lot of different people that say there is no definite right answer, but I guess there are some wrong answers. So one of the things I saw was somebody mentioned go with 3 to 4 times the diameter of your electrode size, and that you can't go wrong. Well, that might make sense. I'm assuming the diameter would be the ID of the cup because the wall of the cup's kind of thick here. So I've got a 3/32 electrode in here now, so that's around 93 thousandths. So if I multiply 93 thousandths by 4, I get 372, and by 3 I get 279. So 279 to 372, so that's 317 ID. That's 430, so that's over 4 times the diameter of the tungsten. And that's 460. So interestingly enough, I came across a question that somebody posted on the weldingtipsandtricks.com website, and this is those of you who've seen the welding tips and tricks videos on YouTube, know Jody, and you know, he definitely is an experienced welder, so I think it would heed me to pay attention to what he has to say. And this is what he gave for a reply. He said, when you're working by yourself and paying for your gas, one of the pluses to using a small cup is that you can set the flow meter low and use less gas. If I am welding 1/8 inch or thicker, I often use a 4 or 5 cup and only 10 to 12 CFH, which is cubic feet per hour. And let's see, and it works fine on carbon steel. So it's really about oxidation, because he goes on to explain larger cup size is more important for things like titanium, where you've got to have a much better coverage of that shielding gas. And then he also talks about how there's going to be situations where you need a smaller cup just because you're trying to get into a corner or a tight bevel. So with that being said, I think I'm going to put a number 5 cup on this tungsten. Oh, okay, so I just figured out how to find out the size of these cups. So the cup number is actually 1/16 of an inch times the cup number gives you the ID of the end that where the gas comes out. All right, so if I take 5/16, if I take 5 and divide it by 16, I get the decimal equivalent of what this opening is. So this is a number 5. I don't have a number 6. This is a number 7, and this is a number 8. I think I'm going to rethink my original thought to go with a number 5, because I found other charts online that actually recommend a larger cup. I don't have a 6, so I'm going to go with a 7 on this 3/32 electrode. Next thing I have to do is I have to set the stick out. I have to set the distance that the electrode sticks out from the end of the cup here. And again, from what I've gathered online, I want to be 4 times the diameter of the electrode. So since this is a 3/32 electrode, I want 4 times 3/32. So 4 times 3/32 ends up being 375 thousandths. So I'm sure a lot of guys in the trade don't use verniers to set this, but I want to just try and get this as correct as possible. So that should do it. All right, so next I want to talk about holding the torch. And different people hold the torch different ways, but one of the ways that I tend to see a lot of people holding the torch and describe it as the quote-unquote correct way to hold the torch is sort of like this. You notice my grip. And then the cord, always being mindful of where your cord is. Cable, I should say. And then the angle at which you want to hold the torch when you're actually welding. I think I remember somebody saying at one point that theoretically the best angle would actually be straight on. That the more perpendicular you can be to the actual weld pool, the better off your coverage is going to be. But the problem with that is that you have an obstructed view of the weld puddle, so you have to have the torch angled a little bit. So ideally you want to have it angled enough so that you have good visibility of the weld pool, but the puddle. But at the same time, you don't want to have it angled too much. I think the problem with having it angled too much is that you probably have a problem controlling the arc from wandering, and I would also imagine that creates a problem with the shielding gas. Probably 45 to 65 degrees, maybe somewhere in there, or 60 degrees. All right. And then the last thing I want to talk about before I go over to the machine and talk about my machine settings is I want to talk about starting the arc or initiating the arc. So there are 3 ways in which we can initiate arc, okay? And not all TIG welders are capable of doing all of these types of starts. I'm going to start with the most common, And this is often the poor man's TIG welder is nothing more than a arc welder that's had a TIG torch attached to it and some other plumbing fittings to get the gas flowing, and you can literally do some TIG welding with an arc welder. So anyways, in order to start initiate an arc with one of those welders, you have to use what's called the scratch start method. And the scratch start method for TIG welding is, well, it's a little like striking an arc with stick welding. But in this case, you're only momentarily contacting the base metal. And it's almost, I would call it, they call it scratch start because you're kind of like scratching the surface. And it's almost like you're striking a match. And the idea is that you are going to contact that base metal, and that's going to close the circuit and start the current flowing. And if you just hold this down and you start the current flowing, you're going to have a problem where your tungsten's going to want to stick to the base metal. So the idea is that we want to make contact to initiate that arc, but at the same time we want to keep the tip moving and then pull up. So we're only going to take a little scratch and pull up, and once the arc is lit, then we can start to build our pool and then start welding. So that's scratch start. And with a little practice, just about anybody can do that, I think. The second type of start is called lift start. So some people think that lift start is just a variation on starts for a variation of starting with scratch, only that you just hold it in one spot, and because you touch it, it's going to create a constant, the current is going to flow and you're going to start an arc when you lift up. In reality, machines that are designed for lift start actually have a special circuit built into them. And what actually happens with those machines is when you put them into the lift start mode, so to speak, it's almost like you're arming them. And what happens is when you touch the electrode to the base metal, you complete the circuit, but at that point, the high current to start an arc isn't flowing. What the welder is waiting for to happen next is it's waiting to sense when this circuit is broken. So what happens is, as soon as I lift up on this, I break that electrical connection. There's a circuit in the welder that immediately senses that that connection has broken, and at that very instant, it energizes the electrode. So in effect, what it does is it creates a situation where the electrode is not in direct contact with the base metal at that point, but it is so close that an arc is able to initiate. So if that makes sense. So with a machine that's designed to do this, you can hold this down and it's not going to sit there burning your tungsten into the base metal, and that the arc's actually not going to even initiate until you break that connection. So hopefully I did a good job of explaining that. So if you don't have, I guess the point here is that if you do not have a lift start mode on your TIG welder, then you don't want to try using a lift start. If you do not have high frequency start, which is the last thing I'm going to talk about, and you don't have lift start, basically you've got a scratch start TIG setup, no doubt about it. All right, so lastly we'll talk about high frequency. So the way high frequency works is there's actually another circuit in the welder that creates a high frequency, high voltage that is induced onto the welding cable. And what that does is that is able to cause a spark to jump from the tip of the electrode to the ground base metal. Once the electrode is within a certain distance, once it's close enough, without touching it, once it's close enough, that little spark will jump. That spark, when it jumps, will actually cause a very low path of resistance to develop in the airspace between the tip of the electrode and the base metal. And that will allow the high current to flow and initiate the arc. You know, and on modern inverter machines, the high frequency can be so intense that you can be pretty far away and get that high frequency to jump. But once you get close enough, then it'll actually also allow that arc to travel, and the arc will light, and you can basically weld. And on depending on how you set it, if you set the high frequency for start, what will happen is once the arc lights, then the welder circuitry will sense that the arc is initiated and shut off that high frequency because it's no longer needed. That's in the start mode. And then if you put the high frequency in continuous mode, you actually can keep the high frequency running during the whole welding process. And that's for use in AC welding when you're, it gives you extra cleaning action. But we're not going to get into that because, again, this is noob welding, so we're going to be playing around with mild steel. And I'm going to use high frequency start because my machine has it. And it's going to keep me from hopefully contaminating this tungsten too often. Okay, it's time to talk about gas. So the type of gas that I'm using is pure argon. And pure argon is used in TIG welding for most applications. There are some applications where you want to use an argon-helium mix. I'm not going to get into that because, again, you're here for noob welding. And the noob is doing mild steel. So the next thing I need to be cognizant of is my gas flow rate. And my gas flow rate is pretty much determined by the size of the cup that I have. And we just talked about that the cup kind of follows the electrode size for the most part. So I should be looking at around, for the size cup that I just put on there, I should be looking at around 15 to 20 CFH, which is cubic feet per hour. So cubic feet per hour it's basically a ratio. It's sort of like how speed is a ratio of time and distance. Well, cubic feet per hour, hours obviously time, cubic feet is volume. So it's a certain volume over time. So if we were theoretically, if we had this hose and we were filling up 1 cubic foot bags, we could literally, if we could just take the hose and fill one bag and immediately fill the next bag and immediately fill the next bag, and we didn't lose any during the transfer, we could fill at 20 cubic feet per hour, we could fill 20 of those bags in 1 hour at the rate that the gas was coming out of here. This gauge right here is a pressure gauge. This tells me what the pressure is in the tank. This gauge up here is my flow gauge. Now, I don't know if you could see this, but there's actually, it says CO2 on this side and it says argon on this side. And the difference in the numbers being staggered a little bit, that must have to do with the fact that the two gases have different density. That's the only thing I can figure out. I'm not sure why, but it's basically, like, for instance, the 20 for argon is right here, and the 20 for CO2 is just a tiny bit above it. I mean, just a smidge. Anywho, so I want to be looking at this one over here. And what's in there is there's a little ball in there. And what happens is, when I turn this gas on, okay, what happens is that little ball right there, when I turn on this flow meter, when the gas solenoid on the welder opens, the flow will cause that ball to rise up to a certain point. And then I can adjust this right here to adjust the amount of flow so that it shows 20. So I'm going to turn my welder on so that I can demonstrate setting this. Just letting you know that this is my welder turning on, because it's probably somebody's going to probably think I just started up a Cessna airplane in my basement. When I first power up my welder, it opens the gas solenoid. So again, this is the argon scale right here. That's 30, so 20 is down here. You notice how that ball is still staying up and now it's going down? That's because my welder has a built-in post-flow timer. And what the post-flow timer does, the post-flow timer keeps the gas valve open when you stop welding and the arc is extinguished. It keeps the gas flowing long enough to keep that weld pool, that molten metal pool, bathed in the shielding gas until it has a chance to solidify. It's protecting it from oxidation. Now on my welder, the duration of that post-flow period is actually set with this knob right here. You can see it actually says seconds delay. So that's how many seconds that the post-flow continues after the arc is shut off. So I might be left to wonder where I should be setting this, but as luck would have it for me, the manufacturer of this welder, they actually had this dial calibrated, so they actually have, I don't know if you can see that right there where my finger is, but this literally says tungsten size. So right here is 40 thousandths, right here is 1/16 of an inch, and right here is 3/32, and over here is an 1/8 inch, and then there's even bigger ones over here. But the point is that if I set this right there to 3/32, maybe even a smidge more, okay, that actually corresponds to about 15 seconds of post-flow. So I don't know, some of you guys might think that's too much or too little. I'm not sure. But according to what Miller and Airco thought back in the day when this was made, that's what they came up with.